Hello students, welcome back. Let's resume our discussion on normal subgroups. Previously, we went through a couple of trivial examples here. By the way, here's a reminder. What do you mean by a normal subgroup? The left coset and right coset must be the same all the time for every element of the group capital G. And you can reduce it into this inclusion. And then in terms of elements, you can rewrite like this or that. So basically, this is going to be the criterion that you should be looking for. Okay, the first example, the trivial subgroup is always normal. The trivial subgroup, that means a subgroup that consists of only one element, the identity. So n is going to be E, so G inverse, what is it? Yeah, we just get E, so that belongs to the trivial group again. So yes, it's normal. Too trivial. How about the next example? All subgroups of abelian groups are normal. Oh, that too is trivial. You can always go back to this. Gn and Ng are the same because the multiplication itself is commutative. But you can do it hard way if you want to, like this. G and G inverse, and switch the order of these two because we are dealing with an abelian group. So we get back to n, which belongs to capital N. So yes, everything is normal there. However, these two examples are just too trivial. Let's consider some non-trivial examples. And all these are going to be non-abelian groups, so please brace for impact. Okay, let's begin. The alternating group, AN, is a normal subgroup of the symmetric group SN. What is an alternating group? It's a subgroup of a symmetric group that consists of even permutations. Remember, every permutation can be decomposed as a product of transpositions, but the number of transpositions required is not unique. However, the number is unique modulo 2. Whether it is even or odd is definite. So take all the even permutations that form the subgroup, and that's called the alternating group. So how do you prove that the alternating group is normal subgroup of symmetric group? Well, basically you have to do this. Oh, what did I do? Okay, and then G belongs to Sn, and then n belongs to an. N can be rather confusing because it coincides with a number. So let's do it this way. Sigma for arbitrary element of the symmetric group, and alpha for an arbitrary element for alternating group, S and A respectively. And then let's see, this is going to be replaced right here as sigma, and then sigma, and then alpha, and then this is going to be an. That's the question, isn't it? So we have to consider conjugation. How do you test whether this thing belongs to an or not? The number of transposition required for this, and the number of transposition required for that, the number of transposition required for that, you have to add them all up, right? So this expression here, and let's get out of this bold business. Come on. Why do I have the other color? Okay, that's what I wanted. So this can be written as some transpositions. And then this is some transposition as well. And that too is going to be some transposition. And how many transpositions are there that are multiplied? Well, you have to add them all up. And I claim if I add them all up back to AN, so we have to have even number back again. That's what you have to prove. So how do you prove that? The total number is back again, even. We know this one is even. What about sigma and sigma inverse? Well, this may require a certain number of transpositions. And what I claim is the sigma inverse requires the same number as sigma. Why is that? Think about that. Got the idea? Well, here's the answer. Alternating groups consist of even permutations, so it can be written as a product of even number of transpositions, 2m transpositions. Now, sigma can be written as a product of transpositions, say k, and what's sigma inverse? It's the same multiplication, just backward. If you apply the inverse formula, you get this inverse and the next inverse. All these should be inverses, but these are transpositions, so inverse of transposition is itself. So we just get back. So what do we have? K transpositions, another K transpositions, and then 2m transpositions. I get 2m plus 2k. That's an even number. Next example, the rotation group is a normal subgroup of the dihedral group. Remember the dihedral group? It's a subgroup of a symmetric group because that's a permutation too, but this one comes from rigid motion only. It's basically a necklace dynamics. Consider a necklace like this, and then rotate. You can rotate any number of times, and you can also flip any number of times in any order. You can do this infinitely many times, but you don't get infinitely many elements there because it's a permutation one way or the other. Total, you're going to get actually 2n outcomes, but that's not the core issue here. The key issue is this. The rule, which I just highlighted in some other color, like green. Yeah, okay, all right. How does that work? Well, here's a visualization. Flip, and then take a rotation. Okay, row composition tau. So flip and then rotate versus rotate backward and then flip. Tau row inverse. So this is a composition. So from the right and to the left, that's how the application is done. So right first and then left. Backward rotation or clockwise rotation and then flip. And then flip and then forward rotation or flip and then counterclockwise rotation. End results, these two are the same. Please check. So if I use this rule to these two and then repeat k times, then that's what you're going to get. And then these two cancel out. So the arbitrary element of this cyclic group, rho to the k power, ended up with another element, rho to the negative k power of the same cyclic group. So this cyclic group, or the rotation group, is normal. The conjugation stays in the same group. So we just went through another non-trivial example. The rotation group inside the dihedral group. The next example here, this one we already went through in detail in lesson 6, so I'm not going to redo that. When we studied coset and Lagrange theorem, we went through this very example. In S3, which is the smallest non-abelian group there is, we have all the elements here. The first row is actually a cyclic group given by a 3-cycle sigma. And then we have 3 more additional subgroups. Actually 4 more, but 3 more additional proper non-trivial subgroups. Okay, there you go. The cyclic group generated by tau 1, the cyclic subgroup generated by tau 2, and cyclic subgroup generated by tau 3. And then, of course, there are 2 more, the trivial group and then S3 itself, but those are out of consideration. And these are not normal. You can rigorously prove those through brute force computation, which we did in lesson 6. And then we can prove that this is a normal subgroup. I'm not going to redo that computation. Please go back to lesson 6 and go through those. And even in lesson 6, I skipped a lot because we are talking about highly unpleasant and brute force computation. Yeah, you can do all those computations. They're all elementary. It's just that they're so tedious. So if you really want to, you can go back to all those computations. But if you don't, then okay, you can just take my word for it. This will turn out to be normal. You can check all those left and right cosets and then see if those are all the same. And then as for these, yes, you can find at least one counterexample. Okay, all right. Now the final example here. GL, which is an abbreviation of the general linear group, that's a multiplicative group of all non-singular, so invertible n by n real matrices. And yeah, it's real because this notation specified R here, and we call it the general linear group. And another thing is the special linear group, Sn and R, and it's the set of all n by n real matrices with determinant 1. That forms a subgroup of the general linear group. And it turns out S is a normal subgroup of G. So what do you have to do? Any element of this general linear group, and then any element of this special linear group. Yeah, excuse me, I forgot this universal quantifiers. I have to consider A, B, A inverse, and does it belong to S or not? That's the question. So how do you prove something belongs to S? That is, determinant of this is 1. That's the question. Well, the proof is actually pretty simple. There you go. Non-zero determinant is 1. And then this is inverse, so 1 over that determinant. So you just get back to 1. Okay, so much for the examples.